Hi guys, Dr. Burns here. We are going to start chapter 2, which is where we're going to get into some different techniques for solving differential equations. And specifically in this chapter, we're just going to focus on solving first order differential equations. And remember, a first order differential equation is a differential equation that just contains a first derivative, and that's it. So go ahead and make sure your cell phones are put away and you're ready to take notes and pay attention for the next 10 minutes or so. First, I want to just remind you of something we talked about in Calc 1. And if you were in my class, I gave you the acronym PVA. If you were not in my class, it's okay if you've never heard it this way or you don't remember it right off the bat, but that's okay. PVA stood for position, velocity, and acceleration. So that just gave us a way to remember the relationship between those three concepts in physics. If we know the position function, the velocity is the first derivative of the position, and then acceleration is the derivative of velocity. Notationally, we would write it this way. If s of t is the position, v of t would be ds dt, the velocity, and then the acceleration would be dv dt, or the second derivative of the position. All right, and we're not going to use that a whole lot, at least not at this point, but I'm just bringing that up to kind of launch this next example. It says that Newton's law of motion, or second law of motion, states that force is equal to mass times acceleration. So we could write that equation this way: force equals mass times acceleration. If we were to write this as a differential equation, because remember, acceleration, we just said, is dv dt. So I'm going to rewrite this now as force equals mass times, instead of acceleration, I'm going to replace that with dv dt. And if you get close to the Earth's surface, this equation becomes, and what I did just move the dv dt over to the left side, the mass times dv dt to the left side, and that equals mass times g, where g is the acceleration due to gravity, b is some positive constant related to air density, and v is the velocity. Now, I don't expect you to know these concepts from physics. You may not have ever taken a physics class directly, although I encourage you to do so if you have not. But I'm bringing this example up just to talk about the idea of separating the variables. And you might have touched on this briefly in Calc 1, maybe a little bit in Calc 2, but we're going to get really more into the weeds with this in this section. So when we separate the variables, that's a technique we can use to solve some basic differential equations. And let me show you what I mean using this example. Now, before I dive in, I want to just remind you here that m is some constant mass, whatever the mass of the object is. G is also a constant, that acceleration due to gravity. I think, and I'm not a physics person, but I think it's 9.8 meters per second squared. You don't have to know that. Just know for this illustration that G is a constant. And of course, B is some constant, like I said, related to air density. I have no idea what that would be. I guess it depends on, I don't know, the object, whatever. It doesn't matter. The point is, I want you to just keep in mind as we go through this example that your only variables are V and T. V is velocity, T is time, of course. All right, so what do we mean by separate the variables? Let's look at the algebra that's involved here. You can think of dv dt as division. It's not technically that, but you can treat it that way when you're using separation of variables. So what I like to do is I like to multiply that dt, or whatever that independent differential is, to the other side. So I'm going to write this as m times dv equals mg minus bv times dt. And what we want here is we want anything that contains a v in it to be over on the left side with the dv term, and if there was anything that contained a t, we would want that to be on the right side with the dt term. And of course, constants are fine to be with anywhere. It doesn't matter about those. But to get this term with the v in it to the other side with the dv, I can't subtract because this is multiplication. I can't add or anything like that. So what I'm going to do is I'm going to divide by this entire expression that's in the parentheses. I'm going to divide both sides by that mg minus bv. So now what I have is I have m over mg minus bv times dv, we can think of it that way, equals, and now there's just a 1 in front of the dt. So what I've done is I've separated the variables. Remember, m, g, and b are all constants, so v is a variable, t would be a variable. So I've separated the variables on each side, and now once I've done that, I'm going to integrate both sides according to their respective variable, and that's why that separation of variables is so difficult. Now, I'm going to do a little bit of hand waving here. I'm going to solve this left side. I'm going to integrate this left side, rather, using some techniques that you should have covered in Calc 2, but we'll cover them in more detail in class. So if you don't get where all this is coming from, please do not worry about it. But the integral of this left side for now, like I said, you can just take my word for it, is going to be m times negative 1 over b times the natural log of mg minus bv, and I'm putting that in absolute value because of the natural log, equals, now the other side, remember, if this is a 1, the antiderivative for that would be t, and then we need a c in there somewhere. So because c is just a generic constant, when you're using the separation of variables technique, I always just put the plus c on the side with the independent variable, whatever that is. Okay, and then what you want to do once you solve using separation of variables is, in general, you want to try to do this if the solution can be written explicitly where it's the dependent variable solved by itself. You want to go ahead and do that. I'm going to do a lot of algebraic hand waving here, take my word for it, but this ends up becoming mg minus bv equals ce to the negative bt over m. And I realize right now you're looking at that saying, where in the world did she get that? I have no idea what just happened. Please do not worry about that right now. That is not what's important. Just focus on what my end result is. Hang in there. Remember, my job is to get v by itself. I'm trying to solve for b, or v rather. So from here, I'm going to subtract the mg to the other side. So I end up with this expression. And then I'm going to divide by negative b. So this becomes v equals, let's see, it's going to be I'm going to rewrite this, mg minus, because the signs are going to change, ce to the negative bt over m all over b. And if you want to write this as v of t, because that's really what that is the solution to the differential equations. Let me write that a little neater. That's the solution to the differential equations using separation of variables. Like I said, all of this stuff right here, we can go over that. We'll talk about that and practice that some more in class. That is not what I want you to worry about. Here's what I want you to worry about, okay? I want you to make sure you understand how I initially separated the variables by multiplying dt to the other side, how I divided by this mg minus bv to get the v term with the dv on this side, and then I integrated both sides with respect to their individual variables. And then the last step was I solved for the dependent variable v. We will talk about that more in class. Do not worry. In fact, I've got another example here that's a little more straightforward. But let's just go over what we're doing. This is called separation of variables, and these are called separable differential equations. Can't spell that word. Separable differential equations. So whenever we can algebraically separate the variables, so we have dy dx equals some function of x and y, or x and or y, it may not have both variables, but if it can be manipulated algebraically to write the left side as a function of y dy and the right side as a function of x dx, that's when we use the separation of variables technique. Let's do one more example. Solve this differential equation. Now this one is a little more straightforward. Maybe I should have started with this, but that's okay. What we want to do here is we want to get this y squared term with the dy, and we want to get this dx term with the x minus 5. One way to think about this is literally just cross multiply. So we can write this as y squared dy equals x minus 5 dx. And so now I have the y squared with the dy, I have the x minus 5 term with the dx, and I can integrate both sides. So I get y cubed over 3, And then normally we'd put the plus c, but remember you're just going to put that on the side with the independent variable. So this becomes x squared over 2 minus 5x plus c. And as I mentioned, you want to try to get that y by itself, but when it involves a radical, because this would be a cube root, I usually just leave it the way it is. Now I'm not a fan of that 3, so I'm going to multiply everything through by 3 and write this as an implicit solution. Y cubed equals 3x squared over 2 minus 15x, and you don't need to write plus 3c because remember c is just a generic constant. It doesn't matter at this point what c is. Sometimes they'll give us an initial condition that we can use to plug in and solve for c. We'll do some examples with that in class, but right now this is all you need to worry about. So I will see you in class. We'll do plenty of practice with this, and I'll see you tomorrow.